Let's see if we can tackle this free response question that covers concepts from units 1, 4, 5, and 6. You can see we're given the graph of function g, and g is a piecewise defined function. It has a linear component, a semicircle component, and then a horizontal line component. In the statement of the problem, we're told that the function g is defined on the closed interval from -4 to -8, which we can see in the graph. The graph of g consists of two linear pieces and a semicircle, as shown in the figure above. Let f be the function defined by f of x equals 3x plus the integral from 0 to x of g of t dt. So f is this new function, and it's made by taking 3 of x and adding the area under the curve of g from 0 to whatever value x is. That's an accumulation function. And so then we have 4 items here that we're going to address. You can see that letter A is, we're supposed to calculate f of 7 and f prime of 7. So we'll start attacking A, B, C, and D on the following slides. So you can see that I've adjusted the slides so that I have a little more room to work here. We're going to attack letter A, and the first thing that we're asked to find is f of 7. Well, if we simply substitute 7 in for x, f of 7 would be 3 times 7 plus the integral from 0 to 7 of g of t dt. So I've got two things to do here. 3 times 7, that's pretty straightforward. I'm going to just make that 21. But then I also have to find the area from 0 to 7 under or between this curve and this x-axis here. So this is part of the area, and then I also have this section here. So the area is, made of these two pieces. The first piece is this piece here, the semicircle. That is negative area. So I'm going to put minus. That's a circle of radius 3. So the area of the whole circle would be 9 pi, but we have a semicircle, so that's 9 pi over 2. This piece here, that's positive area, and that is just 3 units, so that's going to be plus 3. So, simplifying here, this is 24 minus 9 pi over 2. And I've got that part done. So let me just highlight that there. Makes me feel better about being done with my answer. Okay, now let's draw a little line here just to separate my work. Let's talk about f prime of 7. Well, we know f of x is this function right here. So we can write out the expression for the derivative. F prime of x is, well, the derivative of 3x is 3. And then using the first part of the fundamental theorem of calculus, I know that I can take the derivative of that integral from 0 to x. That's just going to be g of x, right? We just take that x and stick it in where t is. And so if I want to calculate f prime of 7, this is going to be 3 plus g of 7. To find g of 7, I just go out here to 7 on the graph, and I figure out what the y value is. The y value is 3. So f prime of 7 is 6, 3 plus 3. And we're done with that one. Let me highlight my answer there so you could believe that I'm done. I guess it's not done until I highlight it. Okay, part A wasn't too bad. We'll check that off the list, and then we'll move on to the next slide to attack part B. So in letter B, we are asked to find the value of x in the closed interval at which f attains its maximum value, and then we're supposed to show some justification. When I think of a closed interval and finding a maximum value for a function, a continuous function, I think of that extreme value theorem. And so it might be a good idea for us to just quickly take a look at the function values at the endpoints, right? We check the endpoints and critical points when we're dealing with the extreme value theorem. So f of negative 4, let's just compute this. That's going to be 3 times negative 4, which is negative 12, plus the integral from 0 to negative 4. Ooh, I'm going to switch that, make that minus the integral from 0, or from negative 4 to 0. So I just switched the limits of integration and changed the sign on the definite integral. Now, as you know, that's the area between the curve and the x-axis from negative 4 to 0. So there's a little triangle there. That value is, what is that? 4 times 2 over 2. So that's 4. So this is negative 12 minus 4, which is negative 16. Let's just make a note that that is less than 0. Okay. Notice f of 3 is going to be 3 times 3, which is 9, plus the definite integral from 0 to 3. I don't have to change the limits of integration because 3 is on the right. And let's see, from 0 to 3, what part of the circle are we talking about there? That's this part. So that is negative, 9 pi over 4. That's a quarter circle. So this is 9 minus 9 pi over 4. And I know that's going to be, that little fraction there is less than 9. So this is greater than 0. I'm just going to make a note that that's greater than 0. Now, as long as this function doesn't have any critical points, or we check the y values on the critical points it has, then we know it looks like this thing's always increasing. Let's just double check. The derivative, which we've already talked about, is 3 plus g of x. And if we're going to look for critical points, we just set that equal to 0. So that occurs when g of x is negative 3. G of x is negative 3 right here at x equals 3. So this implies that x equals 3, and we've already checked x equals 3. So by the extreme value theorem, x attains its maximum at x equals 3. Not because it's a critical point, but because it has the highest y value. Right? We said this was a positive number. And that's higher than negative 16. Another way to look at this is notice that the derivative on the interval negative 4, 3 is always either positive or 0. Because on negative 4, 3, g is between negative 3 and 2. So the derivative is going to either be positive or 0. The function is never decreasing. So the max is going to occur at that right-hand endpoint. Okay. Let's take a look at letter C on the next slide. So for letter C, they want us to either find the value of or state that these limits don't exist. So there's two limits. We're trying to find the limit as x approaches negative 0 from the, let me start over. The limit as x approaches 0 from the left of g prime of x, and the limit as x approaches 0 from the right of g prime of x. Okay, so g is this graph here. And we get derivatives off a graph by looking at the slope. So g prime on when we're less than 0, right, from the left side is going to be the slope of this segment. Well, it doesn't take much to figure out that that equation is a line. And let me just note here that g of x is going to be, that is just negative 1/2 x, right? It has a y-intercept of 0. So g prime is just negative 1/2. So the limit as x approaches 0 from the left side of g prime of x is just negative 1/2, right? We can figure that one out pretty quickly. So I'm okay on the left side. I check that one off. I get negative 1/2. Now, let's talk about the right side. Intuitively from the graph, you can see that these slopes are getting bigger and bigger, and that there's going to be a vertical tangent at x equals 0 when you're looking from the right side. We can also show that algebraically, but this limit's going to be undefined. Let's just talk about the algebra real quick. So when x is greater than or equal to 0, g of x is the semicircle below the x-axis shifted over 3 units, right? Because the center is shifted over here to 3, 0. So that equation is negative square root of 9 minus the quantity x minus 3 squared. And we can simplify that to the square root of, if you multiply this out, that's going to be 6x minus x squared. The derivative of that thing, if you use the chain rule, is going to be 3 minus x over the square root of 6x minus x squared, and that thing is negative. I'm going to reposition that negative sign. That looks a little funky. Let's just put it on the denominator. Okay. And then as we look at the limit, as x approaches 0 from the right side of g prime of x using this formula, we're going to get, by substitution, we're going to get 3 on the top, and we're going to get 0 on the bottom. And this is a does not exist. Okay. So intuitively, we can see from the graph that this sucker doesn't exist because there's a vertical tangent on that left side of that circle. But algebraically, we can also see that we get an undefined value here. It does not exist for 3 divided by 0. So that's letter C, and we'll wrap this thing up with letter D on the next slide. So in letter D, we're simply asked to compute this limit. F of x plus 7 over e to the 3x plus 6 minus 1. Well, when we do limits, oopsie. I got to switch to the pen here. When we do limits, and we're going, what, to negative 2? The first thing we try is substitution, right? And so let's go ahead and try that and see what happens. E to the 3x plus 6 minus 1. So essentially we need to do f of negative 2 plus 7 and figure out what that equals. Well, f of negative 2 is 3 times x, so that's negative 6 plus the definite integral, so minus the definite integral from negative 2 to 0. G of t, and then plus 7. Well, I just need to figure out this area here. Negative 2 to 0, that's going to be 1/2 base times height. That's a 1. So this is going to be 0. The whole thing. Because negative 6 minus 1 plus 7 equals 0. All right. And then this e to the 3 times negative 2 plus 6 minus 1, that's e to the 0 minus 1. So that's also 1 minus 1, which is 0. So this thing is indeterminate, right? And we usually put a smiley face when we have indeterminate form because that means we can do L'Hopital's rule. We can keep doing math. We love to keep doing math. Okay, so let's see if we can figure out the derivatives on these things. So by L'Hopital's rule, let me write that down. So this is L'Hopital right here. The limit is going to equal the limit of the ratio of the derivatives. So the derivative on top is just f prime of x plus 0, so that's f prime of x. And on the bottom, we're going to have to do this derivative. This is 3e to the 3x plus 6. Okay, now, we can do substitution here. The denominator is going to be 3. And f prime of negative 2, we already did f prime of x. Don't forget that f prime of x was 3 plus g of x. And so this is just going to be 3 plus 1, which is 4. So this limit has a value of 4/3. Yeah, baby. All right. Took a while, but we got it. Okay, so lots going on in this problem. We had some accumulation. We've got some limits, understanding maximum values on a closed interval, the extreme value theorem. So plenty of concepts in this problem, but I think we spent enough time on it. If you have any questions, you know where to find me. Take care.